All right, Honors Chem, today we are going to learn about phase changes and the energy that goes along with them. We're going to introduce the concept of equilibrium today, and we're going to, hopefully, I think I'm going to do this in another video, teach you how to use phase diagrams as well. So we have a lot of things going on today. So we're going to start with phase changes. Now, before in probably junior high, they didn't call the states of matter phases. They called them states of matter, solid, liquid, or gases. In chemistry, we use the word phases. So we can have the solid phase, the liquid phase, and the gas phase. So I want to go over some vocabulary here with this, and I also want to go over some of the energy that goes into changing these phases. Okay, so let's start with solids, okay? Notice here in this solid phase, we have this graphic of these molecules in this perfect, nice crystalline form. Notice we have the little orange vibration symbols here. These molecules are fixed at a point and they can only vibrate about a point. So they can't move very much. They can just kind of shake and wiggle about that point. So notice there's not a lot of space in between the molecules. All the molecules are packed in there really quickly. So normally we think about a solid melting and going to a liquid. Notice when we go to that liquid, we have a little bit more space and we have a little bit more motion. That we don't have a perfect arrangement anymore either. The organization of this molecule becomes less, okay? So melting takes energy, right? So this melting takes energy. So this is what we call it's endothermic and exothermic. So I'm going to define these words first. So exothermic is a reaction that releases energy. So it's an energy releasing reaction. And endothermic is a reaction that absorbs energy. Okay, so melting absorbs energy. It takes energy absorption to go from solid to liquid. So melting is what we call an endothermic reaction. Freezing, though, when we freeze, we actually release energy. Energy gets given off, and that water, for example, if we go from water to ice, it goes to a colder temperature, so we're releasing energy. So that is an exothermic reaction. Okay? Then we normally think of liquids then vaporizing to gas. Notice in the gas molecules, there's a lot of space between the molecules, and the molecules are moving very quickly, and there's even less organization in a gas molecule setup than in a liquid or a solid molecule. So to go from a liquid to a gas, it takes a lot of energy to vaporize that. So it takes energy, it absorbs energy, so vaporization is an endothermic process. Whereas if we condense something, we've all walked out on the grass in the early morning where the water has condensed on the grass, and it's gone from the water vapor state to the water liquid state by cooling down with the cool night air. So that is an exothermic reaction. Condensation. Okay, now this is probably something that you haven't talked about a lot. Sublimation is where we go from a solid directly to a gas. Okay, we go from this nice orderly arrangement to a very chaotic, fast-moving arrangement. That indeed takes a lot of energy. Excuse me. So sublimation is extremely endothermic. It takes a lot of energy. Okay, but deposition, where we go from a gas to a solid directly, we release a ton of energy. We slow down those molecules and we release energy. So that is an extremely exothermic reaction. Okay? So, we also, I should probably introduce this to you. Solids we abbreviate with an S in parentheses. Liquids we abbreviate with an L in parentheses. And gases we abbreviate with a smaller g in parentheses. Okay? So, there are our definitions of the different phase changes and the energy that it takes to do them. Okay, so let's scroll down if it will let me. Okay. In a given sample of a liquid at any given temperature, the average kinetic energies So the average, now this is the key, the average kinetic energy of all the molecules is constant. It doesn't mean that all of the molecules have the same kinetic energy. It's kind of like if I gave you guys a test or a quiz. Does everybody get the same score? No. But can I create a class average? Yes. And do the class averages differ very much from class to class? No. But the individual scores may differ, okay? So in actual fact, the individual kinetic energy varies greatly. So the individual kinetic energy of each individual molecule can vary greatly. So we're going to talk about what it takes to evaporate or go from the liquid state to the gas state really quick. So in order for a molecule in a liquid state or a liquid phase to evaporate and become part of the vapor or the gaseous state or phase, that molecule has to have two things happening. Okay? So the very first thing is that molecule has to be on the surface of that liquid where it goes to where the gas phase is. So the molecule needs to be on the surface. The surface of the liquid in order to evaporate. And the second thing that the molecule has to have, it has to have enough kinetic energy to break the intermolecular forces of the neighboring molecules so that it can become free to become in the gas state. Okay? So the molecule has to have enough kinetic energy to break the intermolecular forces of the neighboring molecules. To break free. Okay, so I'm going to call these forces of attraction. Now, it's kind of like, how many of you guys, when you were little, played the game Red Rover, Red Rover? I know a lot of you guys don't play it anymore because it usually ends up with a bunch of broken arms. But if you've ever played Red Rover, you've got a line of kids holding hands with each other, calling their friends from across the field to come over and run and try and break through the wall that you guys have created with your arms holding hands. Now, you know that the kids that are able to break through that wall are, one, running pretty fast, and usually target their hit to be right where the hands are, right? So they're right on the surface and they're running fast. So we need to be on the surface And we need to be moving relatively fast so that we can break those those intermolecular forces of the neighboring molecules so that we can break free, kind of like Red Rover, Red Rover. So let's think of this. This is a distribution of the kinetic energy. So we've got kinetic energy down here and the number of molecules in a drop. We're going to say that this is a drop of water that's sitting on the counter. Okay? Notice some of the molecules in that drop of water actually do have enough kinetic energy to break through those intermolecular forces and become free. Now, how many of these molecules in this section right here are actually on the surface? Probably very few, but a few of them are, so they will evaporate and they will vaporize and become part of the gas state. Okay, so here's a thought question. If I have a drop of water like this on a counter, so this is a drop of water, and I leave it on the counter, and you come back 20 minutes later, is that drop of water still going to be there? Probably not. So if the average kinetic energy of all molecules is constant, if I take one of these molecules that has enough kinetic energy to escape, and I take it off and it becomes a gas, what did it do to the average of the molecules still left? If I take this molecule away, isn't the average going to shift down a little bit further? So how does this average become constant? How does it stay constant? I want you to think about that for a second. Okay, do you have any ideas? Think about in the summer when you hop out of the pool and your body is wet when you first come out of the pool. What does your body feel like? Even though the day might be really hot, it might be 95, 100 degrees outside, you're cold. Why are you cold? Because the water that's evaporating from your skin is taking heat from your skin. So the reason that this molecule or this drop of water can evaporate fully off the kitchen counter is it's taking heat from the counter or whatever is surrounding it, or its surrounding materials. Have you ever touched a kitchen counter or a kitchen table right after it's been wiped down and dry? It's cold because the molecules that have evaporated off have taken the heat from that counter or that table and used it to evaporate. That's how a swamp cooler works as well. We take some water, we let it evaporate in the air, and it cools down the air because it takes the heat out of the air for the energy to evaporate. Okay? So only a certain number of molecules have enough energy to escape these attractive forces of their neighbors, these intermolecular forces, and evaporate. These right on the far side of the graph. Yet a drop of water will completely evaporate if left undisturbed on a tabletop or a countertop. How do these other molecules acquire enough energy to evaporate? Where does this energy come from? We already talked about this. It comes from the surrounding materials. The energy comes from the surrounding materials. Okay? So, is it possible for a gaseous particle that has evaporated to collide with the surface that it just left? And if that gaseous particle's kinetic energy is low enough at the time of the collision, could it rejoin the water? Okay, so that can happen. If it comes from a container that's open, there's little chance of that happening. But what if my container's closed? In a closed container, this type of collision is really, really possible. It really increases. In fact, a point is reached where just as many molecules of gas are returning to the liquid state as are leaving the liquid state for the gas state. Okay, in this closed container, the rate at which the molecules evaporate equals the rate at which the molecules condense. Or in other words, if I have the liquid state, it can go to the gas state right here, and the gas state can go back to the liquid state. If this is equal, okay, we can have an equal reaction going forward and backwards. Okay, this kind of an reaction arrow is a reversible reaction. Okay, so we will be using a lot of reversible reactions because honestly, most reactions are reversible. I can go forward and backwards. Okay, so here we go. This will, oh. Okay, so here's another diagram. If I have an open container, that water, as it goes to the gas stage, will eventually come out of the container and I will lose molecules. Yeah, I might have a few molecules that actually do not make it out of the container, but eventually, if I leave this container out on the counter or the table forever, the level of the water is going to continue to go down, and eventually one day I'm going to come and that bottle is going to be empty. But if I plug this up, if I put a stopper in here or a top or a cap on it, eventually the number of molecules that are leaving, you see these ones that are leaving, are going to be equaled out with molecules that are coming back to the liquid state. Okay? And this is where we have, let's see, we're going to pretend like this is water. So I would draw this equation as H2O, not mercury, H2O, liquid, going back and forth with H2O gas. Okay? So this is how we draw a double-sided arrow. Some people draw them like this as well. It really doesn't matter, just as long as you show things going both directions. Okay, so we say that the system is in what we call an equilibrium condition. It's a special type of equilibrium because it's called dynamic equilibrium. Okay, and the reason why it's called dynamic equilibrium is the molecules are still coming and going, okay? The molecules are still going from the gas state to the liquid state, and they're still going from the liquid state back to the gas state, or vice versa. We could also do it from a solid to a liquid, or whatever phase change we wanted. We are always going to be changing molecules. Individual molecules are changing, but the rate going forward is equal to the rate going backwards. So the overall number of molecules in any given state does not change. Okay, so that is the definition of dynamic equilibrium. We still have individual molecules changing, but the rate of the forward reaction is the same as the rate as the reverse reaction. Okay, so let's talk a little bit about our friend Mr. Le Chatelier. Obviously French, you can tell from his name. Okay, so here's Le Chatelier's principle, and we use Le Chatelier's principle a lot in chemistry. Okay, so if I put a stress on a system, so when a stress is placed on a system, and the stress can be something like we will change the temperature, we can change the pressure, we can change the volume, okay? Those are all stresses that we can put on this. We could even change the concentration, okay? Those are all things that we can do to stress a system, okay? So when a stress is placed on a system at equilibrium, the system will shift in such a way to relieve the stress. Okay? So, we're going to talk about how these systems will shift to relieve stresses. So, all liquids in a closed container will reach dynamic equilibrium with the vapor in that closed system. But this happy system at equilibrium can be disturbed by placing a stress on the system. So what are the stresses that we can place on the system? We can place a system, we can change the temperature, we can change the pressure, okay? If it's not a solid, rigid container, we can change the volume. We can even change the concentration. Of products or reactants, okay? So let's think about this. We're going to use heat as a stress. We're going to change the temperature, right? We're going to use heat. So what happens if I take liquid water and I heat it? Okay, so we're going to heat this. So we're going to actually use heat or energy as a product or a reactant. So if we're heating it, we're going to use delta H as our symbol for heat or energy, okay? If I'm heating it, I'm using H or heat as a reactant, right? That's part of what starts that reaction. So what happens if I heat water? Doesn't it vaporize? Doesn't it boil eventually? Yeah, it does. So it's going to shift to make more gas. Okay? So I want you to think about this being kind of like a balance, like a classic Greco-Roman balance where we have a pan here, and we have a balance with a pan here, okay? So I want you to think of one pan as the reactants, and I want you to think of the other pan as the products. Okay, so we're going to, okay, if I add more heat doesn't that make the reactant side, if I add more heat, doesn't it make this reactant side a lot heavier? So it's going to make this pan, let's see, it's going to make this pan go down, right? It's going to make the reactants pan go down. So what do I need to do to make this even out again? I need to make this side heavier, right? Okay, so what do I need to do to make this side heavier? I need to make more products to make that heavier. That's why this will shift to make more gas, to equalize things out again. Okay, so we think of our products and reactants, and what we do either puts more or less in one of these pans and shift things. And what do we need to do to make those pans equal again? That's how we're going to determine Le Chatelier's principle. Okay, so to help determine this, we decided whether energy was required or released when evaporation occurs, right? So when evaporation occurs, energy is required. That's why we put it on the product side, because anything that is endothermic, delta H is going to be a reactant. It's not the product side, reactant. Anything that is exothermic, delta H, or the heat, is going to be on the product side. Okay, because heat is released. It's part of the products. Okay, so if energy is required, we place the symbol for heat, delta H, on the left side. We place it on the reactant side. If energy is released during the reaction, it is an exothermic reaction, and we will place delta H on the product side. We all know that it takes energy to go from a liquid to a gas. That's why we put it on the left side, because it is an endothermic reaction. Okay? Just a reminder from the previous page, evaporation is required. Okay, so it is required. So it is an endothermic reaction. Okay. It is required. Okay, energy is required from the surroundings. Thus, it is an endothermic process. Okay, it's an endothermic process, and delta H should be on the left side of the equation. Okay, so now consider Le Chatelier's principle. Will the equilibrium shift towards the heat or away from the heat? It's definitely going to shift away from the heat because we've added a ton of extra. So we're going to have to shift this way. So we are going to create more gas. It's going to shift away from the heat. We will create more gas. Okay? So we say, because that shifted right, we drew a right facing arrow, we see that that reaction shifts right. That doesn't need to be there. So I should say shifts without the apostrophe. Shifts right. All right. So, well, all right. So this shifts right. Okay, now we're going to consider this equilibrium. We've got solid water to liquid water. Okay, is this process exothermic or endothermic? To go from solid to liquid, Do I need to heat up that system or do I need to cool down that system? I need to heat it up. So this is an endothermic process. So I'm going to put the delta H on the left-hand side, part of the reactants. Okay, how can I shift that to the right? How can I get that to move to the right? I could heat it up, right? Okay. All right. Solid water has a greater volume than liquid water. It's very, very unusual that a solid has a greater volume than liquid, okay, from which it came. So if pressure is applied, what happens if I apply pressure? Water is going to relieve the stress by going to a smaller volume. Okay, so remember that solid water has a greater volume come on, let me do this. Solid water has a greater volume than liquid water. So if I put pressure on ice, it's going to go to a smaller volume. Remember, a smaller volume is going to be on the liquid state. So that means that this is going to shift right because liquid is smaller. That's why ice floats, by the way. Okay, the equilibrium will shift to the right and liquid water will form. Okay, so how many of you guys have ever been ice skating? Okay, when we ice skate, we put a ton of pressure. All our weight is on that tiny little blade there, creating an immense amount of pressure. And because of that pressure, we shift that equilibrium to make liquid water. So under our blade, it's not actually ice, it's liquid. And you're actually hydroplaning on water when you ice skate. And that's how ice skating works. We're actually shifting that equilibrium from solid to liquid using immense pressure. And we are making water, so we hydroplane. Okay, melting point. The melting point of a crystalline solid, let's do this definition really quick and let's get a lighter color. Okay, the melting point of a crystalline solid is the temperature at which the forces holding the crystal lattice together are broken and it becomes liquid. Notice I didn't say it's a specific temperature because we can get things to melt at all kinds of different temperatures if we change the pressure, just like we did with this water and ice here with pressure of the blade of the ice skate. Okay? The amount of energy required to melt 1 mole of a solid depends on the strength of the forces keeping those particles together in the solid. Because hydrogen bonds are between water molecules are very, very strong, a relatively large amount of energy is required to melt ice. Okay, ice has a very high melting energy. Okay, however, the energy required to melt ice is much less than the energy it is required to melt table salt because ionic bonds are much stronger than hydrogen bonds, right? So melting salt is going to be much, much more energy. Okay? Boiling point. Let's talk about boiling point. Now, boiling point, we usually say, oh, it's 100 degrees for water. But once again, we can change that with the pressure. Boiling point is really the temperature at which the vapor pressure, remember the vapor pressure is all the molecules vaporizing from the surface of a liquid. So the pressure of those molecules coming off the surface of a liquid equals the external or atmospheric pressure. So that vapor pressure of the molecules coming off the surface of the liquid has to equal the atmospheric pressure pushing down, and that's when the liquid will boil. Okay? So, that being said, is it possible for water to boil at a temperature less than 100 degrees? If I change the pressure, could I get it to boil at less than 100 degrees? What's the approximate boiling point of water at a typical day of Salt Lake City? Remember, our atmospheric pressure is not the standard pressure. The standard pressure is 760 millimeters of mercury. We have lower pressure, therefore our boiling point is going to be lower because our atmospheric pressure isn't very as high. So instead of having it be 100 degrees, here in Salt Lake, it's about 98 degrees. Okay? I'm going to add a video showing how you can get things to boil at room temperature. Okay? We can actually boil water at room temperature if we get pressure low enough. Okay, vapor pressure versus temperature. Okay, so different things have different vapor pressures. Ethanol, which is a type of alcohol, evaporates a lot quicker than water at the same temperature because it has less intermolecular forces and it doesn't create nearly as many hydrogen bonds as water, so it will vaporize quicker. Those intermolecular forces aren't as strong. So ethanol will boil at standard pressure at about 75 degrees, where water will boil at standard pressure at about 100 degrees Celsius. Notice the different types of intermolecular forces very much depend. The boiling point depends on those. Okay, so I want to define normal boiling point. Now, the thing that we really want to stress is the normal in here. Okay? The normal boiling point is the temperature. The temperature at which the vapor pressure of a liquid equals normal pressure, which is sea level, which is 760 millimeters of mercury, or you could say 1 atmosphere, or 101.325 kilopascals. What else do we have? We have a bunch of different ways that we can measure pressure, okay? 14.7 psi, pounds per square inch, 14.7 psi, or pounds per square inch, all kinds of pressure. Okay, so the vapor pressure has to equal normal pressure or standard pressure, which is sea level pressure, 760 millimeters of mercury, or 1 atmosphere, or 101.325 kilopascals. Okay? So it has to be normal pressure to be the normal boiling point temperature. Okay? It's also possible for water to boil at temperatures higher than 100 degrees. If I put a ton of pressure over that water, that vapor pressure is going to have to be even higher to match the atmospheric pressure. Okay? So if the pressure above the water is in excess or greater than 750 millimeters of water, a greater amount of energy is required for that vapor pressure to be able to push those molecules apart and to escape. Okay, so here's an example here. Water boils at 100 degrees sea level. If I go to Pikes Peak in Colorado, which is the highest peak, I believe, in the lower 48, it is about 85 degrees Celsius, because we're about 4,400 meters above sea level. If I go to Mount Everest, which is the tallest mountain above sea level in the world, it goes down to about 71. That's just because of lack of atmospheric pressure, because the higher we go up, the less atmosphere we have pushing down on us, so the less atmospheric pressure. If you've ever gone hiking in the mountains, you'll notice that it takes a little bit longer for your stuff to cook up in the mountains just because the water, even though it's boiling, is not quite as hot because it's boiling at a lower temperature. Okay? It's also important to note that different liquids have different boiling points. Liquids with really low boiling points have particles with low intermolecular attraction. Okay, so if I have a low boiling point, I don't have a lot of intermolecular attraction to keep those molecules next to each other, low IMFs. Okay, these substances therefore evaporate more rapidly and are said to be volatile. Okay, am I going to be able to write? Okay, and then liquids that boil at high temperatures have high intermolecular forces, and they have very high attractions to their neighbors, so they are considered non-volatile. Okay? So remember, low IMFs mean very low boiling points and high volatility. High IMFs mean very high boiling points and mean very low volatility. All right, we will talk about phase diagrams. Maybe I can actually write this. So low IMFs and it's gonna freeze. All right, so we will talk about phase diagrams next time and teach you how to read them. All right, have a great day. We'll talk to you later. Bye.